Welcome to the afternoon session in numerical analysis. This is the section in numerical analysis, and Anna-Karin Tornberg will chair this session. And we'll have this afternoon 3 speakers. I'm pleased to introduce the first speaker, Professor Anna-Karin Tornberg. Anna-Karin Tornberg is a professor in numerical analysis at KTH since 2012, after being a faculty at the Courant Institute before. Her research concerns the development of numerical methods for the solution of PDEs, with a particular emphasis on boundary integral methods for fluid involving particles and drops. She graduated in 2000 from KTH, the same year that she was awarded the Leslie Fox Prize in Numerical Analysis. Please join me in applauding Professor Tornberg as she is taking the floor, giving a talk on FFT-based spectral Ewald methods as an alternative to fast multiple methods.
Thank you very much. So I would really like to thank the organizers, or whoever suggested my name, that I would be able to speak here. It's really an honor. So this is the title of my talk, and I will get to that, but I would like to start a little bit broader, motivating what I do with an application, and then eventually getting here. So this is a system that we are looking at. It's in microscopic system, droplet-based microfluidics. So you have little tiny water drops in oil. And you have some substance or biological material in this system that you'd like to analyze. So these are built and used. And from a fluid dynamics point of view, that means that you have surface tension forces acting on the interfaces. Often you add some surface active agents, surfactants, to stabilize the drops so they shouldn't coalesce. And of course, the oil and water has different viscosities. Because of this, you get not only discontinuous pressure across the interfaces, but also velocity gradients are discontinuous. And with the moving and deforming drops, you have a time-dependent geometry. But these are very small scales, and because of that, the Stokes equations are applicable. And this means that you can reformulate them as an integral equation. And I'll get back to why you would want to do that, maybe. But first, a look at the Stokes equations. So they look quite simple. Here they are. But they do get more complicated. It gets more complicated to solve as we add this jump condition at the interface, leading to these discontinuities that I described. And this interfacial force that I'm stating here is for a clean drop, meaning no surfactants. You modify it if you need surfactants. If we're going to do this as an integral equation, then why would you? Well, it actually has several advantages. So one is that you have integrals only over the interfaces of the domain, like the drop surfaces, not in the bulk. You don't have to solve in the bulk. And the discontinuities in pressure, velocity gradients are of no concern. They're really embedded in the formulation. And you don't have to care about the viscosity ratios. It enters only in the coefficients. The velocity will be divergence-free by construction. So I started out working on PDE-based methods on these kind of problems. And then these things, once you put in an interface condition like this, it's very difficult to get high accuracy. So it's wonderful when you see this list and you think, oh, you get all of this for free. That's great. Now, of course, it's not really for free, because when you get something good, then you have to pay with something else. So there are 2 challenges that always come up with integral equations, which is that you will need to handle the integration of singular and nearly singular integrals. And also, you will have dense matrices that you need to work on. And I will discuss both of these today. And the second topic here is the title, with the long title on Spectral Ewald method comes up with this. And I should just say that in this case, we're happy with the Stokes equations. Of course, Navier-Stokes has a broader applicability, but it is a current research topic, how to extend integral equations to Navier-Stokes in the most suitable way. Okay, but if we want to work with integral equations, we have to think about fundamental solutions. So the first fundamental solution of Green's function for the Stokes flow is the so-called Stokes-let. So it's given here, and you see that the order, it's like a 1 over r orders. So it's like the harmonic Green's function, but it is a tensor quantity. And we will also see another fundamental solution appearing, which is the stress-let, which has a different form. So we can write down an integral equation for this problem. So here we have one. This is an equation that is for points on the boundary. So this is on the drop surfaces. We would need to solve such an equation, where this single layer potential includes the Stokes-let, the double layer potential includes the stress-let. If you're not familiar with these, you don't have to look so much at the details. The important thing, we have certain integrals we have to evaluate. We have to enforce this on the drop surfaces or interfaces and solve for the velocity. This is sufficient for us to know how to evolve the interfaces, how to evolve the drops. If you want to know the velocity inside any drop or outside of any drop, we can compute that, but it's like a post-processing step. You don't need to do it within your time evolution, but you can get that. So this is the equation that we need to deal with. So when we work with integral equations, we usually discretize them by what's called the Nyström method. So you have your integral equation on the interface, and you say, OK, I'm going to enforce it at certain points that this holds, your collocation points. And if you pick those points to be the same as your quadrature points, it's called the Nyström method. And this is typically what we use. And as I said already, we are reducing the number of unknowns because the grids are only on the surfaces. And another important point is that we're working here with a well-conditioned formulation, or a second-kind integral equation. The one that I showed is of that kind. And what does it mean? In practice, it means that, if you have a certain setup, a certain geometry, and you discretize it, when you refine that geometry, the condition number of your system matrix will stay constant. So in all other methods, finite difference, finite element, first-kind integral equations, the condition number increases with refinement. But this is not the case here. And that has the practical implication, if you use an iterative method to solve a linear system, then the number of iterations will not increase as you refine your system. So the computational cost will really scale with the cost that you have of the matrix vector multiply that you do in each iteration. OK, so to look at this, I know that first one was a little bit harder to see. So let's look at the simpler integral equation, which is we want to solve the interior Laplace problem with Dirichlet data. So the solution for any point in the domain omega can be represented by this double layer potential. You could use a single layer potential, but if you want the second kind equation, this is what you use. So you can represent it like this. Then you take the limit as this point goes to the boundary, and to get your equation on the boundary. So you get the limit, you have this term coming out with a double layer. So this is the equation that you get. Identity plus something compact, a second kind integral equation. So this will be two steps. First, we solve this equation for the density mu. And then, for any point in the domain when we want to know the solution, we evaluate this integral. This is the two steps in this case. And it's quite common when you do work in 2D that you rewrite this thing in complex variables. It looks quite differently, but you just have to figure out what does this really becomes, and how do you write the scalar product in complex variables, and if you go through that exercise, you could convince yourself that this is equivalent to what I just wrote. OK, so this is usually what we discretize. So going back to this Nyström idea again and quadrature, in this example, we would split the curve here into panels. And on each panel, we will put a distribution of points that comes from some quadrature rule. And in my case, that would be a 16-point Gauss-Legendre rule. So we discretize these panels with that. And then when we do that, then we can solve, we discretize the integral like that, and we enforce the equation at the same point. That's the Nyström method. Then we can solve this, and we're going to assume we've solved it to high accuracy with a double layer density. It's not hard to get high accuracy. This is like a 32nd order scheme, and it converges, if it's smooth, it converges very fast. Okay, so then we have solved. So we assume we've solved for mu very accurately. Then we're going to post-process and compute the solution everywhere in the domain. And now I'm going to show you not the solution, but the error in the solution. It's very typical, of course. So what we can see here is that if we're far away from the boundary, we're very accurate. You see, we have 15 digits of accuracy or something away from here, or maybe 13, 14, I don't know. But as we go close to the boundary, this is a zoom in, the errors grow very quickly. So what is happening here? Well, your evaluation point Z here sits here. And if Z is close to the boundary, it means that this 1 over tau minus Z is going to get very peaked in a neighborhood here. And it's not resolved by a quadrature. And then you get these large errors. And of course, it can be very interesting to actually estimate these errors, and very useful also to have that estimate. So we have worked on that. So we derived, because if you start looking at the classical error estimates for Gauss-Legendre quadrature, they greatly overestimate the error, so you can't really use them. So we found this approach in the literature to use contour integration and residue calculus to actually work with this. And then we applied this to this kernel and derived error estimates for flat panels. But in reality, of course, we have some curve, and each panel is not flat. So at first, we did some simple mapping to a flat panel, and we got pretty good results. But then we said, OK, but let's do it more carefully. And we really constructed a numerical map with these 16 points that we have on a panel to the 16 points that we have here. And once we have defined that map, we can say, if we have a certain evaluation point here, what evaluation point it would correspond to here. And then we would plug it in to the estimate that we have for a flat panel. So it's a combination of doing, because normally we don't have this maybe parameterized. We'd have to do this numerically and then using this estimate. And this was done with Ludwig of Klintenberg, most of the work, and then we've also recently extended it to Stokes equation with Sarah Poisson. OK, so if we look at this, now again, I'm plotting the errors. The measured numerical errors are the colors. But the contours are actually the estimates. So we were quite amazed. You see the black contours here? This is the error estimate that we produced. So it's not an upper bound. We can make an upper bound too, but then we did more detail. We did it to be like a practical estimate that we can really use. So you see how close it is. And also for the Helmholtz equation, it's very close. Something else to know about this error is that here I plotted it for Stokes equations. This also has the estimates showing a very good agreement. But I also show here when you have 25 panels and then 50 panels. And what you see is that the area, how close you can get to the boundary before you get larger errors, is shrinking. You can get closer to the boundary with more refinement on the boundary. But you still get large errors here. So you certainly have a problem. So it doesn't go away by itself, by refinement. And this is a general issue. I showed this now in 2D, but of course, if you do it in 3D for the Stokeslet, you have a similar issue. And you really need some special methods to do that. So we have contributed a bit to this. And the error estimates, we have used more extensive. You can take this further for other terms, and so to actually be able to do a method where we can pick parameters in some expansions to guarantee a certain tolerance. But I'm not going to really talk about that. But here, in 2D, I would say the methods are really good. So here, we did an extension by a method that was first introduced by Helsing and Ojala for Stokes. And comparing to the previous picture, if we apply this method, we can completely kill off the error all the way up to the boundary. So you can get very high accuracy. And in 3D, you have some quadrature by expansion method that was introduced in 2D, but we took it up to 3D by pre-computation. And you can actually also get this. I'm just showing it in the upper plane, and this is the regular quadrature. But I would say that in 3D, for general surfaces, this is still an active research topic, how to do this best and how to get rid of these errors and to do it also in an efficient way. Okay, so here I'd like just to show a few examples, because now we know that we can do this nicely. We can handle when things are close by, because when we have, I did this example for post-processing that were close by, but when we solve the integral equation and we have drops close by, that means that we also have to handle this already in solving the integral equation. So this is an example in 2D, which is quite unphysical. This is a rolled up drop. This has also surfactants on it. That's why it has a concentration. And then you have small drops in here. And there's no background flow, so it's only the surface tension forces that are active. So all the drops want to get, well, this is 2D. They want to get circular, because that's the minimum energy state. So the surface tension will drive them to a circular state. So this is how it goes. So as I said, of course, not such a physical problem, but it's testing the robustness of the method and the way that we can handle these really close interactions. And the pre-computed QBX method we used here in such simulations, where all these particles are the same shape and also axisymmetric. So we can pre-compute some and store very little and make it a very efficient method and get high accuracy for these kind of packings. So this is how we'd use it. But for the general surfaces in 3D, we have here implemented or some modified version of a state-of-the-art method first introduced by Leching and others. But here there is an issue of parameter selection, how to optimally choose parameters, etc. So we are working on trying to extend our error estimates to 3D. We'll see if we can succeed. We won't get them as precise, but hopefully they will be useful. So this is something that we're working on. But this is generally in the field, this is something that's open. How do you best deal with general 3D surfaces? So with this, so I've already showed in 2D this discretization. Of course, in 3D, if we have to discretize this, we also get some discrete sums. So we have some quadrature rule, and we apply it. And I've incorporated some quadrature weights into here. So if you're going to sum these sums, you have n terms, n points to sum over for each evaluation point, yielding order n squared work. So this is what we mean by a dense matrix. I mean, you could view this as a matrix multiplying a vector entry. So then these would be the matrix entries of your matrix. And it only decays as 1 over the distance. So it is going to be full. It won't have a lot of 0 entries in there. So then you have to deal with this somehow. So, and of course there are solutions for it, and the most popular solution is to do fast multipole methods. Well, that's the most common, pioneered by Gringer and Rockland. But you can also use FFT-based methods. And as I mentioned before, if you do work with well-conditioned integral equations, the total work is really given by how fast you can do your matrix vector multiplies. So it's going to be almost linear in the number of unknowns. So now I'm getting closer to actually talking about what these spectral Ewald methods. So they are FFT-based methods, spectrally accurate. I'll explain what all this means. But I'm going to discuss them for electrostatics. So that will be like thinking about the harmonic Green's function instead of the Stokes light. They have the same kind of decay, but all terms here are simpler, and the formulas are simpler, but they are quite similar. So in the electrostatic calculations is used a lot in molecular dynamics, because you need to compute the electrostatic potential and the force, things like that. So then you look at sums of these kinds. So you say that you have a number of charges, if you sum, you assume it's a charge-neutral system, so if you sum them up, they sum to 0, and you want to compute the electrostatic potential. And this is the kind of sum that we had before. That would be the one over R Green's function that you'd see here. But then I've added another sum. And in electrostatic calculations, it's very common, the most common is to have triply periodic boundary conditions, because you want to reduce edge effects when you do, like, you want to somehow simulate infinite large systems. And so you do triply periodic ones. But you can also want other periodicities. And certainly for Stokes flow, we might want the problem to be periodic only in one streamwise direction or in 2 directions. So it's good to be able to do all of this. So Ewald, in the 1920s, already worked on this kind of sum and developed a summation formula that bears his name. And the idea is, so if you think about this sum, where it comes from, you can think about it solving a Poisson equation with a superposition of point charges, like the direct delta functions in the right-hand side. And so then you can think about it going about writing this as convolving it with a Gaussian and adding it onto it. So this part here, if you think about the contribution for this, would be like the difference from the contribution from a point charge and something smooth with the same total charge. And the idea is that you move away from that, it's going to be exponentially small. So you get something that decays fast. The second part, suddenly you have a superposition of, these are Gaussians. You have a superposition of Gaussians in your right-hand side of the Poisson equation for a periodic problem, which is very nicely solved in Fourier space. So this is what's being done. So this is the classical Ewald sum, the way it looks. And so this is the real space part and the Fourier part. This is a correction term that you have to add. This psi here is a decomposition parameter. It means that if you increase psi, this converges faster, this one slower, and vice versa. But the idea of an accelerated method to actually compute this faster is to use an FFT, use FFTs to compute this sum, and then you can get the new cost balance, pick a different psi, and in total, if you do it right, you can get your order n log n method. So this is the idea. So our method is part of the family of particle mesh Ewald methods. Sometimes one uses that frame just to mean a specific method. But if you just think about the structure, I mean just the structure of the method. So it's a very simple method in structure. So basically what you do, so you have a number of point charges. Okay, so you take some interpolation of window function and you interpolate them onto a grid. Then you just take an FFT to go to Fourier space. You apply a scaling. I call it here a modified Green's function. You do an inverse FFT to go back to the grid, and then you use the same interpolation window, whatever function you want to call it, to interpolate from the grid to the evaluation points, which might not be, of course, at grid locations. And the methods, they all just differ by the choice of this spreading or this window function, and the modified Green's function here depends on this choice. So you will have essentially two kinds of errors. One is that you've actually truncated the sum, an infinite sum, so you'll have a truncation error, but you will also introduce some additional approximation errors. So you have to think about what those are. And so today, so our set of methods, we started doing the triply periodic problem, but for Stokes and then for electrostatics, but then we've been extending it in different directions. So what I want to talk about today is how to, like a unified framework for dealing with all the way from triply periodic down to free space problems. How can you deal with those? But first, I just want to mention this choice of window function that I was saying. So there's a very popular method here of the SPME method. It's called the smooth particle mesh Ewald methods, where B-splines are being used. And they have a certain and if you do that, you keep them fixed, then really the approximation errors will depend on the grid size of this grid that you use to interpolate to. So you get some fixed order h to the p. And you need to increase the grid size for the FFTs to reduce your approximation errors. But if you think about it differently with these Gaussians, that you can actually scale them differently, depending on where you are, you can scale them so that you get an exponential decay of errors as you refine your grid. So instead of seeing, so this is we did early, so instead of having the number of grid points here, instead of seeing some algebraic 357 decay, you can get this exponential decay of the error. So we have used, as I said, the typical, what we have used before has been to use truncated Gaussians. So you just truncate them at some point. Today I'm also going to include the new window function that we've used. I've called it the Barnett-Magland function. And it's an approximation of the Kaiser-Bessel function, which is a special function that's known for this. The reason to use an approximation is that this one does not include Bessel functions and such that are very expensive to evaluate. Anyway, we're going to have this as a product of one-dimensional window functions, and we're going to assume that we have a window function with a Fourier transform here. So now I'm just going to fill in some details. So these are the steps that I already explained. So here means spreading to the grid. This is your window function. So xn is your location, spread to the grid, take an FFT. If you do that, you'll get this v hat of k here that wasn't there up here initially. So I'm going to compensate by putting the inverse here. Actually, I'm putting the inverse squared, and that has to do with that I'm actually using a w in the last step as well. So I have to compensate for that too. So what I talked about before, doing the spreading, the FFT and the scaling, I said the modified Green's function, it actually only differs by this factor. So this is how the choice comes in. And then in the end, you approximate this integral, and it's a spectral order, and then this is what you do. So then you interpolate back to the evaluation points. But now we want to do this for different periodicities. So if you look at it, I have a D here indicating if it's 0, 1, 2, or 3 periodic directions. Then you have a real space part, the Fourier part, and the self-interaction part here. These two first ones, no, they're here. The real space and the self, they stay the same. Well, the summation is different, but the terms are the same. But the k-space terms differ. So when you have a periodic function, you can represent it with the Fourier series. But when it's not periodic anymore, then it's a free space. You have to go to Fourier transforms, and you get integrals instead. So if you look at it, the expression is exactly the same. But instead of having a sum here, in the triplet periodic case, over all 3 discrete variables, we have in the doubly periodic case, we have 1 non-periodic direction. We get the 1 integral. We have 2 non-periodic direction, only 1 left. And here, there are no non-periodic directions. So these are the kind of expressions that we get. Here, of course, this is singular when they're all 0, for example, but it's integrable. You could go to spherical coordinates, what you like to do. But if we separate out the terms, and this is for the 1p and 2p, where these are both 0, or this one is 0, we can write them like this in 2 terms. And if you do that, you do have closed forms for these. So they are special functions and so you can write them out. But the question is, what do you do to do something fast with this? So for the doubly periodic case, the first idea was to say, okay, but we have a domain. Let's just extend it and make it longer in that domain and see how it goes. And that is not so accurate, but you can add a correction term to make it more accurate. But then there was also another method just appearing, but they really work starting with this. If you evaluate these integrals and you get these special functions, it's based on regularizing and periodizing these functions. So our approach is going to be very different. We want to discretize the integrals on the regular grids, but we have to think about it here. So we have singular integrals. If we let the discrete wave numbers be 0, we're going to have a singular integral. So how do we deal with this? And also the question is now, it's not a discrete sum anymore, it's an integral. So if we replace it by a sum, it's a quadrature problem. So how fine resolution do we need? Do we need to upsample at all? So we have to think about these things. Well, if we look at first the free space case, well, then as I said, the Fourier part is really the Poisson equation with the superposition of Gaussians. So this is simply the solution to a Poisson problem with the superposition of Gaussians in 3D. And in the singly periodic case, if we look at what it becomes, really, if you look at the 0 mode, K1 is equal to 0, for this last part here, it is the solution to a two-dimensional free space problem. And in this case, we have a one-dimensional free space problem. So this is what it is. But how do you solve free space problems with FFTs? This is not obvious. So if you look at the Poisson equation, and you can write the solution in this form, it's a convolution with a Green's function, the harmonic Green's function, or in Fourier space like this. But of course, this is singular, so it's nothing that we want to discretize right off the bat. Now we're going to do something here. We're going to say, let's assume that we have a box of some size, I call it L tilde cubed. And then we assume our right-hand side is compactly supported within that box, and that we seek the solution only in that box. Then the maximum distance of any argument here, x minus y, is going to be square root of 3 times L tilde, maximum distance in the cube. And then we set a truncated Green's function to be equal to g if the argument is less than this maximum distance, and to be 0 elsewhere. Well, then we haven't changed a thing, right? We haven't changed anything. So then you can ask, why would that be useful? Well, the useful thing with this is that you actually get this Fourier transform that has, oh, this should be a g, that has a finite limit. So instead of the Fourier transform for the full problem, as we truncate the Green's function, we get the Fourier transform that which has a finite limit. And now we can just take this one and discretize it on the regular grid and actually get spectral convergence on that. So this turns out to be very useful. So we follow this approach. This is on all. Of course, the triplet periodic we don't need. We don't have any integrals. This is the one that you just saw, the free space one. And then for the others, we follow the same approach so that when the discrete wave numbers are 0 and we have our free space problem, we're going to use, we're going to use a modified function here. And this is just the limit that we have computed. So the second question to answer then here is that, so what do we need to do with these ones? Now, if these are non-zero, right? So now we're taking care of the 0 ones. So now they're non-zero. So if we look at this integral, we introduce a capital K, and we think about integrating this. Now I'm skipping the complex exponential. But if I just consider this one, then we can actually say, again using some complex analysis here, we can actually say exactly what the quadrature error will be for this. And so if we look at what parameters we have, so our discrete wave numbers are actually scaled like this. So, but if we want to look at integers, we have a corresponding k bar. And then in the free space direction, we're going to use a domain that's L tilde. And we would have this scaling, but we introduce now an upsampling factor, 0 padding in real space, to get, then we get this resolution in Fourier space. So you can just think about this as a step size. That's the step size as you want to evaluate your integral in Fourier space. And if you look at that one, what that becomes, if you plug this in, this is the error that you get. So what we can see here, the smallest k-bar, not being 0, is 1. This is going to be close to 1. So this is not sufficient to give us, if we want really high accuracy. So we might need an SF of 4 or 6. So we really need to upsample if we have small wave numbers. But if k-bar is larger, let's say already that it is 6, well, then it's the same as setting this one to 1, and you'll get the same error. So it's not even. So you certainly need upsampling for some mode, but not for all of them. So what we have done, so when we started doing this first, when we went from triply periodic to doubly periodic, we just upsampled all the modes in one direction. But then we were going to start doing the singly periodic, and we said, well, then we have 2 free directions. If you upsample with the factor of 4 or 6 in each direction, that's like the FFTs that are 16 to 36 times more expensive. That's not going to be very appealing. But so then we introduced this idea that we will do different upsampling rates for different discrete modes. So the discrete 0 modes, we know what to do there. The small discrete wave numbers, they will be upsampled, but there is a large chunk of wave numbers where we need not to upsample, where we don't need to increase the size of the FFT. So this is a huge gain in efficiency. Okay, so I've kind of flushed over some parameters, and I'm not going to, and I'm going to, well, mention them a little bit, but we said we started out, we had n charges in some cube. And it's periodic in a number of directions. And we're given some decomposition parameters, some error tolerance. We need to know how to pick our parameters. And we're going to have to choose what grid size we're going to use. We have to choose the number of support. And we have error estimates to aid us in this. And we also need to pick these upsampling factors that I talked about. For this one, for the 0 modes, we know exactly how much we need to pick for the upsampling. And for this one, I showed you this error estimate, but I had removed the complex exponential. I had simplified a bit. So we have that kind of behavior, but we cannot say exactly from those how we should pick them. So we have just some rule of thumb of how to picking the errors. So we are working on getting that more precise. But the algorithm then doesn't really change except from implementation-wise, but not structurally. So what we do again is we have a regular grid, and we extend it in the non-periodic directions. So to fit the window functions, because they're not going to periodically wrap around to the other side now. So we have to make it slightly bigger. That's the L tilde. But then we spread the charges onto the grid. We do an FFT. The difference is now that it's an adaptive FFT. So we upsample different with different modes. And then we knew the scaling. And the scaling, instead of just saying 1 over k squared, as it said before here, it is this different, depending now on the periodicity. In the triply periodic case, it's still the 1 over k squared. Otherwise, it has some modification for the 0 discrete modes to be able to handle them in the same framework. And then you apply your inverse FFT. Again, it's an adaptive one, and you gather from the grid so that you can get this. So when it comes to error estimates, the truncation errors for electrostatics was derived by Colaffa and Perram quite early, and you have these exponential decays of the errors. This is for the real space sum that I'm not really discussing. This is for the k-space sum that we have been talking about. So that kind of tells us how we need to pick our grid size. And then we have our approximation errors that comes from this selection of window functions. And if we look at just the integration of this, if you integrate this by a trapezoidal rule and look at what the error will be, we get 2 terms, which we call the quadrature error, which is kind of how well the Gaussian is resolved on the grid. And then we get another error, which is kind of how much mass we chopped off at the ends by truncating it. So it's like 2 parts. For the Barnett-Maglan function, so far, we haven't been able to derive a similar estimate, but we can see that it follows the same kind of form here. So we're going to set these parameters proportional to p to get approximately the same decay of the 2 terms. And if we do that, we can really see that we get this exponential decay with p of the approximation errors that we are expecting. And that also this new window function is actually needs a smaller p to get down to these kind of tolerances. So it is not going at us rapidly. So this is the total, it's like a timing plot. And so I'm not going to give, this is the only one, I'm not going to go through a lot of different results. But if you see the blue lines here, they are related to when we use the new window function. And the black lines are when we use the truncated Gaussians. So what you can see is that it is indeed better to use the new one. So we found something that was even better than our Gaussians that we tend to like, but anyway. And then the other thing to note is that the triply periodic, you know, we do nothing extra. That's kind of the bare bones case, the simplest case for FFTs. That's always the cheapest. And then you have the doubly periodic, the singly periodic, and so on. And the doubly periodic, it's not, you don't pay much to reduce it by 1. This one is at the most a factor of 2 as expensive, and this is about a factor of 4 if you have rather strict error tolerances. You have the errors down here. So of course, it's really essential in all these ideas. So we can conclude that, of course, the window function, as I said, this is more efficient, so it really depends on, it really matters what window function you use. And you also saw in the, so this is something that we're changing too. And then there are really 2 key ideas that makes it possible, for example, for when you reduce the periodicity, not to see factors of 16 or anything like that, even for high accuracy. And it's really, it's those 2 key ideas, the adaptive 3D FFT, not upsample everywhere, and also being able to do these free space problems with FFTs as like just modifying that scaling in that step, but keeping everything together. This is what lets us do it quite well. Now the question is, of course, how do we extend this to Stokes equations that we are interested in? So we have Ewald summation formulas for the Stokelet for the triply periodic case. It was derived by Hashimoto quite early. And we can use adaptive FFTs if we need to. If we figure it out here, we can use it there. So what do we do with these free space problems? How can we solve them? So if we think about, I know I didn't go very slowly there. One can look at this much more carefully. But this idea that I introduced when I truncated the Green's function and then found the Fourier transform that had a finite limit was done for a radial Green's function. The Stokelet is not radial. But the way we can get around this is that we can write the Stokelet as a differential operator acting on the biharmonic Green's function, which is radial. And with that one, we can play the same tricks as we did for the harmonic one. And when we do that, that means for the truncated Stokelet, we can create a truncated Stokelet in the K-space, just taking this factor, multiplying it with this Fourier transform of the truncated biharmonic that we can derive. And this allows us to solve the free space problem, the complete free space problem. And if we look at what we get when we start reducing the periodicity, if we have only one periodic direction, we get a free space Stokes equation in 2D that we need to solve, so we can follow the same ideas. And if we have 2 periodic directions, we actually get the one-dimensional problem as we expect, and it reduces to a Poisson equation. So we can do that too. But for the Stresslet, we haven't derived the extensions yet. So to conclude, I started out saying, just for you to see a little bit why we are dealing with this, why we care about these fast methods, to say that you do want to use integral equations sometimes. Not only, of course, for Stokes, there's a lot of activity in different wave propagation problems and other things, but they're very beneficial for microfluidic problems, because it gives you a lot for free. You can get very high accuracy. You can do interacting drops and so to high accuracy. But to get the high accuracy, you have to work hard. You have to work, and you have to do these special quadrature methods to really, but then you can really remove the errors in the integration. And if we use a fast summation method, we can then get the computational cost per time step. I didn't talk about time stepping today, which is almost linear in the number of unknowns. So the Spectral Ewald method is then such a fast summation method, and that's what I talked about. And we have an order n log n cost. We can get it when we balance it right with the real space sum for all different periodicities, but it's going to be a different constant. The triply periodic will always be the cheapest. But to get the kind of full set for all of Stokes, we need to do these extensions for the stresslet and the rotlet. We haven't done that yet. So in case you are not interested in integral equations, so you don't think you will use specifically the Ewald method, I think that the ideas that I've introduced here to solve PDEs with any mix of you have some periodic boundary condition, you have some free space in another direction, you can actually apply that to so that this is a way of solving this kind of problem using FFTs. With only a few lines in MATLAB, you've solved such a problem, the Stokes equations or something. So it's a very useful tool to know about, I think. So with that, I thank you for your attention.
Thank you. Any questions? Floor is open. Questions?
Oh, very interesting talk. I'm curious how the number of points on the FFT grid compares to the number of unknowns which is on the boundary.
Oh,
Comment on that.
the number of unknowns on the boundary. So I understand that this is a bit hard to see because I didn't touch on this at all. Because from what I presented, it would seem like it's completely independent on that. But the reason it depends on it, I mean now for the Spectral Ewald method, is that you have the real space part. And the real space part, you have a truncation radius. It decays fast, the real space. This is like the truncation area. It decays fast, the sum, but there's a cutoff radius, RC, that you put. And you have a certain number of neighbors within that ball, so to say, specifically. And so if you have a fixed domain and you start increasing your density of points, then for not the real space sum to grow too fast, the cost, you'd have to reduce your RC. And when you reduce your RC, then you want to increase your psi to get the same error, right? Because if RC is smaller, this has to be bigger. And when psi gets larger, this is decaying slower, meaning K infinity here, which is like m½ in the grid, has to get larger. So it's actually through this connection that you get it like that.
So you ended up with the m cubed being roughly the same order of magnitude as n?
Yes. So it scales with n. So this is what it does. So m cubed goes like n, you can say. But if you have to look at the real space and the interplay between the two to understand this scaling. So the way I presented it today, this is a quite complicated argument. So then you can look at, if you only were interested in doing the Fourier space, it looks like it's completely independent of n, the size of the FFT grid, basically. But it comes from this coupling. Yes.
If not, then I will use my prerogative as the chair to ask you a fundamental question, which I'm not sure I understood. You're using here a window, which is a cutoff of exponential. And these functions do not have exponential decay. They usually have, you have Chauvet regularity, and therefore you have a slow decay. Mm. So somehow, even though it's a cutoff of a window, which is exponential, you are able to recover exponential decay, which is I didn't
So you're thinking about the decay in the Fourier space. Yes. If you take a Gaussian, and if it's not truncated, you just have an exponential decay in Fourier space, like I said with the modes. But if you truncated it, it's not going to be exponential. It's going to flatten out or actually oscillate a bit and go down. Is this what you're thinking of? Yes. So the trick is that this level, when you truncate, has to be low enough so it doesn't interfere. And it actually, it shows here too, it's the same argument here, that you don't want, it translates to this, but I cannot exactly show how, but it translates to this, which also says that if you truncate too much of the tails here, you cannot go below this level. So it's a similar argument, just from different sides. So that's why you have to scale these. So we scale alpha with p, so that when we take more points here and we resolve it better and we do a better job here, we also have to increase this with p to reduce this term. So it's what I mean when I say suitably scaled. This is how you can play with these things. Yes.
If there are no more questions, so please join me in applauding.
Thank you.